Good evening, everyone. I think the attendance would be low today because it's a Sunday, I guess. Uh, in either case, we are going to discuss some questions based on min heap and max heap today, and a couple of other topics. So I hope you got a chance to go through the lecture content related to these topics. In any case, we are going to since we are only few people here, I'm going to give you time to solve the problems yourself this time, and just take as much time as you want, but I want you to solve it yourself because these questions are quite easy. They're fun to solve, and it's important to just clarify your concepts like right now in the lectures, and don't hesitate to interact or ask any questions or clarifications as you need. Okay, so let's just start with the first problem. Okay, so this is basically an algorithm you're given of image processing, and the steps that the algorithm follows, they are given here, and you are asked about the upper bound of the runtime that this algorithm will take. So you have to think about basically what are all the steps that are happening and what can be the worst case complexity of this algorithm. So think about worst case because here it's given that some values can be updated or all values can be updated. So just be careful with the language of the question. Just read it carefully and try to answer. You can either put your, if you have guessed it, put your answers in the chat, or you can just, there are only two of you here, so you can just switch on your mic and tell the answers if you like, whatever you're comfortable with. So just read the question. It's actually related to the content we covered in the first week itself. So it's like a refresher question. So just go through it. Do you guys have any guesses? What would be the answer? Just think about how many operations would be happening in an n cross n array. You're going on each of these pixels and then updating some of the pixels, and each update takes log in complexity. So what would be the worst case? Okay, each pixel update will take log n. Okay, so just think about, like, if you're on I comma j pixel, so it's given that you can either update the whole all the pixels that come in row I and column j. Okay, so there will be n pixels that will come in row I, and there will be n pixels that will come in row j, like column j. Okay, so either you don't update any pixel, okay, or you're going to update all the pixel, like basically the range is from 0 to 2n, so you'll have n pixel in the row and n pixel in the column. So you can at max update up to 2n pixels while you are scanning I comma j, and each of this update is going to take log n. So now think about if each update is taking log n, and the worst case you are updating 2n of these pixels, then what would be the complexity that you'll get? Hmm. Yeah, so it is the C option, O n square log n. So basically the whole concept is that it's an n cross n array, right? So there are n square pixels. Okay, now each pixel, when you're scanning it, you can update like either 0 pixels or up to 2n pixel. Okay, so if you're just going to do a naive analysis, it might you might think that for each of this I comma j pixel, you're going to in the worst case update 2n pixels, and each update is taking log n, so it will be 2n log n. Okay, and this 2n log n you're going to do n square times. So naive analysis tells you that it will be n cube log n, but we are given that each pixel is updated only once. Okay, so overall you're going to only update n, basically this n square number of pixels and log n time, and this update can happen in any of the square in any of the scans. Basically it can happen at I comma j or I dash comma j dash, but the update will only happen once for each of the pixel. So the complexity would be O n square log n. Okay, for if it's not clear, you should ask me right now. Like if it's not clear, why did we between n square log n or n cube log n, if you have a doubt, or even for other options, like if you didn't get it at all or didn't understand the question, just ask. Okay, otherwise we'll move to the next question. Okay, read this question. This is about the union find data structure. I hope in the lectures you found this union find and what it's used for. Like we discussed Kruskal's algorithm last week. So this union find is actually used in Kruskal's algorithm when we are joining basically two set of trees. if you remember, we were looking at minimum edges in Kruskal's algorithm, and we will take in an edge if it is connecting two unconnected spanning trees. So basically, in the union find data structure, you have basically subsets of the whole set, and you can basically create unions of these subsets. Okay, so if you have been through the lectures, there are two ways in which we can do this union find data structure. Like, we can either have an array representation, okay, where the things are represented, like if you have an set S and a set component, then basically each member of set S, which component it belongs to, is given by component I. Okay, we are going to see it. I'm going to show you just to remind you what the two representations were. But there was this array representation and pointer representation. In pointer representation, you have the member of the set S, okay, and there is one more element which points to another member in the set S, and these two basically would belong to a same component. So if you don't remember these things, I'm going to again tell you, like show you like exactly in the slides where these were, so that you're reminded of it. But otherwise, you should just take basically a shot at it. Just see if you can figure it out. Okay. We are going to see the representations of both array and pointer representation in a while. I just want to give you some time to do it without any information. Otherwise, I'm anyway going to give you information on both of these representations, so you can try it again. Yeah. Okay, so I'll just show you the two representations so you're reminded of what exactly they were. So in the array implementation, if you have a set S, alright, and this union find data structure would just be another set which would comprise of subsets of this original set S. Okay, so basically you can have S as 1, 2, 3, 4, 5, 6 till let's say n. Okay, and you'll have this union finds which will have its subset of S. So you can have let's say 1, 3, 5 all the odd numbers and in one set and all the even numbers in another set, and your union find data structure would be comprised of these two components then. So you have component 1 and 2. So what component does each of these elements belong to is given by this component data structure. So component I equal to I. So this is how we initialize it. What does this initialization do is basically create subsets which has only one element, which is that number itself. So you'll have subsets in which there will be 1, 2, 3 until n. Okay, and the component I is basically just the label. So in which component is the ith element present. So that you can just do by component I equal to I. Okay. Now any other union or any other functions that you will do will change the label of each of your members in the set. Okay. So it can be given by a members I. So what will members I represent is the component which is labeled by ith index. Okay, so ith index, what are the members of that component? Okay, so as given in the question, now if you have to reassign basically the jth member, so basically j is an element in your original set S, and you need to put it in the same component as your kth element. Okay, so what would you need to do for this substitution is you'll need to basically change component j. Okay, component j is the label of j, which component will it belongs to. You have to change component j to component of k. So whatever component is present, k is present in, so you have to just put that. Okay, so do you have to change anything else apart from this? Like look at all the arrays that are given here. So component, members, component, and now just look at this array implementation and tell me, going back to the question, what would be the complexity of this operation to reassign component of j and make it similar to component of k? What do you think? How many operations we'll have to do for it, and what would be the complexity of those operations? So if it's not clear to you guys, you can ask me right now. Like if this implementation is not clear, or if you did not understand what will be the exact operations that we'll have to do. Okay, to reassign the component of j and make it similar to component of k, you have to do two operations. So first operation is to just put component j equal to component k, and this is an O1 operation. Okay, and apart from this, you will also need to update the members data structure. So here you have members are equal to I. So what you'll have to do is basically whatever component j was in, so you'll have to do members component j. Okay, and you need to update it. You need to basically delete j from it, and you need to also update members of component k, and you need to add j in that. Okay, So both of these operations are not going to be, so the first operation where you're just doing component j equal to component k, this is an O1 operation. Deleting from the members list and adding to a members list is not O1 operation, and it depends on the size of your members group. Okay, so in the array implementation it is not going to be O1. Okay, similarly for the pointer implementation, in the pointer implementation what you have is, so here for example j, I and l, they belong to the same component. Okay, so along with the members like li, you have one more pointer element which points to basically another member of the set. Okay, and such that the final pointing, like you see here j, so j is going to be pointing towards itself. Okay, and you know that all of these three elements j, I and l, they belong to the same component, and which is the component of j, like whatever component j is in, and which is true also for k here. Okay, so you can represent the grouping of all these elements into a component by using pointers also. So if you need to basically in pointer implementation assign j to the component of k, what you'll need to do is basically first you have to change the pointer of j such that it points now towards k. Okay, and you also need to update all the child pointers. Okay, so again for the pointer implementation also it is not going to be an O1 operation, because you also need to update children of j such that now it points towards the new component which is kth component. So the answer is that both of these operations are not going to be O1. In array representation it depends on the size of the members list, and in the pointer representation it will depend on again how many children were there in the component j's original component and k's component. Okay, I hope this is clear. In case it is not, you should ask now. If you want me to repeat anything or go or give you some more details of these things, you can ask now. Like we can go over it more slowly if you need.
Yeah, it's clear.
Okay, good. Fine, then we'll move to the next question. So this question is related to men heap, and it's a simple question. So men heap is just a binary tree in which all the children of a parent are going to be more than the parent. Okay, so you'll have one value as the root, and whatever comes below it, they are going to be more than this root, and the same pattern will keep on repeating as you go down the tree. So in such a min heap tree, you are asked what would be the time complexity if you have to find the maximum element in the tree. Okay, so you can just make a sample min heap, just make a tree by yourself and try to find the maximum element in it and see what will be the complexity of it. And you have to give it in terms of the total number of elements in the heap, which is n, let's say. So in terms of n, what will be the complexity of finding the maximum element?
Sir, I think it might be
Mm-hmm.
order of n.
Okay, why do you think that?
Sir, there are log n plus 1 levels
Mm-hmm.
in your code.
Mm-hmm.
Now, I think the half of the elements in min heap
Mm-hmm.
would be the leaf nodes.
Yeah, that is true.
Now, uh, in min heap, which is already balanced, and in min heap, basically the tree that is binary tree that is
Mm-hmm. Yeah.
we know that the parent element of
Mm-hmm.
each subtree,
Yeah.
small subtree,
Yeah.
uh, would be smaller than the
Mm-hmm. Children.
smaller than its children.
Correct.
So when we go down the main view,
Mm-hmm.
in each row of
Mm-hmm.
the tree, in
Mm-hmm.
each row of the tree, when we go down, the maximum element. My argument is the maximum element is will be one of the leaf nodes.
Yeah, that is true. That is
So
true.
we just have to check the leaf node.
Okay.
We just have to check the leaf nodes. I know that there are n by 2 leaf nodes,
Mm-hmm.
so complexity should be ordered.
Yeah, that is exactly correct. So if you're given a min heap like this, as Rahul said, all the children are going to be more than the parent node, and you can be so. First of all, what is the maximum element in this min heap? It is this 100 here. Okay, and the maximum will always lie in one of the leaf nodes. Okay, the ending one, because you know that let's say for any of the leaf node, the parent is going to be less than that node itself, right? So if the maximum you have to look for, you are going to look for only in the last nodes of it. So if you have n element as the total number of elements in the min heap, you'll have around n by 2 elements in the last level. Okay, and so you have, and basically you can only constrain it till this level, that it will be in one of the leaf nodes. You cannot say anything further than this, like which part of the tree would the maximum be in, because it can be any of these n by 2 leaf nodes. Okay, so you'll have to basically look for or sort using these n by 2 leaf nodes, and that's why your complexity is going to be on by 2, which is same as on. Okay, fine. So in case this wasn't clear, you can ask any of the steps. Okay, we'll move on. Okay, so look at this problem. You're given a max heap here, okay, and you're given the structure of this max heap. Now you said that this element 57 was inserted in this max heap, and after the insertion it has taken this form as it is given here. So this is an array representation of max heap which is given here, and so you have to basically, the first step would be to make a tree, a max heap like a tree representation out of this array representation. Once you've done that, you have to think about what would be the structure of the heap before the 57 element was inserted in it. Okay, so prior to insertion, what would be the structure of the max heap? So first just draw a max heap given from this array representation, and then try to take a reverse the insertion step. Okay, and once you reversed it, the 57 will be out of it, and all the elements would rearrange themselves, and then you can get your array representation of how the max heap was prior to the insertion. Okay, so just try this question out.
Sir, I think the answer should be A.
A. Okay.
We just have to think about inserting 57 into any of the four cubes here.
Mm-hmm.
I sort of reversed the operation. I know that the correct
Yeah.
approach.
Yeah.
But in order to get a max heap
Mm-hmm.
of, say, for example, let us say with A,
Mm-hmm.
then we will get an idea of other questions.
Yeah.
So when I insert 57,
Mm-hmm.
the first operation is basically put it as lead,
Yeah.
as n lead,
Mm-hmm.
and then let 57
Mm-hmm.
go up
Yeah.
according to its
Value.
जब भी सब ट्री में आएगा तो
Yeah.
we have to check its children.
Yeah.
So it is going to float up,
Okay.
and it has to float up to because it is bigger than all the rest of the elements other
Mm-hmm.
than 87. 87 is
Mhm.
bigger than rest of the elements other than 82. Sorry. So
Mm-hmm.
it has to come up, like in the case of this array, the given array, the
Mhm.
structure of the axis. And now we have 82, 57, 27, 40, 25, 18, 25, 27, 32. Now 57 clearly should be in the left side.
Yeah.
We have 27 in the right side.
Mm-hmm.
Okay. Now I don't think we can change that structure. So either C or D. I was wrong in saying it here.
Hmm.
So either C or D should be the answer.
Yeah.
So अब 27 वाला जो पार्ट है वो वैसा का वैसा ही रहेगा.
Mm-hmm.
I don't think 32. No, I am confused about C and D.
Okay. Okay. But yeah, it was a good attempt. We'll look at. Okay. So, did you guys have any problem making the max heap out of this array representation, or you're clear with that?
So I took from the other route.
Okay. So, given this array representation, this is going to be the max heap. So, you start with 82 at the root node, and then you keep populating basically the nodes in the order of the levels. So, you just keep filling the levels. So, you'll have 57, then 27, okay, and then you come down and keep filling 42, 25, 18, 25, 27, 32. Okay, so this would be the max heap representation of the from the given array. Okay, so now if you want to try and see, like before this 57 was inserted, what would be the tree structure? What would it look like? You try from this structure now.
Okay, 42 would go. और यहाँ पे 32 आ जाएगा. 37, 42, 27, 32, 25. 32, 25. So 32 will come before 25. So
Mhm.
answer आ गया. तो diagram बनना.
What is it? C or D?
Sir, I have forgotten. the-
Okay. If you want to see the options again, it is
Yes.
this.
32 would come before D.
Hmm. Okay. So this would be the tree before inserting 57. Okay, and like try to insert 57 in this tree. Okay, so if you insert 57, it will come as a child of 32. Okay, and now you just need to keep translating this 57 up such that all of its children are less than it because it's a max heap. So if you have 57 below 32, then you change 57 goes up, 32 comes down. Okay, now 42 and 57 again you'll swap. Okay, so 57 will come at this position, 42 you'll get here, which is the tree on your left side. Okay, and the representation of the tree on the right is this. Okay, so just look at this and see if the insertion process is clear to you. First you need to basically get a clarity about the insertion process. Once you have that, you can reverse that process and get this tree. Just look at both of these and see if they make sense. Okay, it's clear. Any doubts? Okay, we'll move on. Next, this will be the final problem of today's session. So you're given again min heap and max heap, and there are two functions basically for calculating predecessor or successor of any given node in your tree. What this predecessor means is basically a value which is just smaller than this node. Okay, so you have to check for value which is just smaller and just bigger than any given node value. For min heap and max heap, you'll need to compute individually and see what would be the complexity of each of these functions for each of min heap and max heap. Okay, like just take your time, and you can use a sample heap like from the examples we had before. Like you can basically have this for your max heap. Okay, and if you're given like 25, let's say, so the predecessor of 25 here would be what, 18, and successor of 25 would be 27. Okay, so this is what you need to compute for the max heap and similarly for the min heap, and just check what would be the complexity of these two things. Okay.
Sir, can I attempt an explanation?
Yeah, sure. Go ahead.
सर मतलब सिंपल लॉजिक लगा रहा हूँ यहाँ पर कि पता नहीं मैं गलत हूँ या नहीं, बट हीप्स में नीचे जाना, अगर सर सपोज मैं बोल रहा हूँ मेन हीप है, तो मेन हीप में if ये तो क्लियर है कि प्रेडेसेसर और जो सक्सेसर है, मेन हीप जिस लेवल में होगा, ठीक है, वो उस लेवल के एक ऊपर या तो उसके ऊपर होगा या उसके नीचे होगा. मतलब ये है कि मेन हीप के केस में जो प्रेडेसेसर है वो नीचे होगा, नीचे वाले लेवल्स में होगा, ठीक है, जो एलिमेंट जिस लेवल में है, और जो सक्सेसर है वो सारे एलिमेंट ऊपर है. हाँ, जो प्रेडेसेसर है वो ऊपर होगा, जिस लेवल पे वो एलिमेंट है उसके ऊपर जाना पड़ेगा हमको सर्च करने के लिए, जो उसका प्रेडेसेसर है.
Or can it also be at the same level?
Yes sir, it can be also in the same level.
But you know that it won't be basically below it.
Yes, yes. The only thing we know that it won't be below it.
But it can be below it in the other branch. So it won't be exactly below it, like it won't be its own children, because all the children would be bigger than it. But even predecessor can come at a lower level if it is
Answer is
not.
C. Yes, sir. I got it. Answer is C. Confirm.
Okay, let others also try and see. I'll tell you if the answer is correct or not.
Really, I'm not sure.
Okay, so let's say this is the min heap that you're given here. Okay, and we need to compute these two functions, predecessor and successor of v. Okay, now think about if you have to compute a predecessor and successor for 25, the node 25 here. Okay, so what is the predecessor of 25 in this whole heap? It is this value 19 here. Okay, and what about successor of 25?
36.
36. Okay, so now look at this min heap and look at this node 25 and the two solutions 19 and 36, and what do you think would be an efficient way to compute these values? Like in the worst case, a naive solution is just to look at all the n values in the heap, okay, and check all these n values and go over each of them one by one and keep collecting them as the predecessor or successor. If you find values closer to them, then you can keep updating it. So that algorithm will take O n time. But think of an algorithm that can be better than this. Can you do it in a way which is better than O n? Okay, Rahul, you are saying log n. What is the algorithm by which we can find these values in log n time?
So mud binary search.
How would you do this search?
Binary search.
And how would you exactly do it? Like you start from 25 and tell me the steps that you're going to follow.
Yes, sir. Yes. So we will. We know that the minimum element or the
Mhm.
maximum element will have to be one of the top. So we have to first find the level. If we take there are log n levels,
Mhm.
so if we take log n time, and then we have to search through that level in order to find mix or match. Because
Mhm.
as far as I understand, the time complexity would not differ as far as you explained it. It can be in the other case.
Mhm.
So in both cases, the time complexity would be the same. So in case of 25, suppose we are finding the min element.
Mhm.
First we check level by level, and then we check in this level, in each level.
Mhm.
So there are log n levels, log n
Mhm.
plus 1, but let us say log n level,
Mhm.
and in each level,
Mhm.
uh, depending on the level, there can be maximum of n elements. You have to take it as time for time complexity.
Mhm.
So once again, it is coming as order of log n,
Log.
because there are two steps. One step is taking log n time, and the other
Mhm.
step is taking log n time. So it should be log n.
No, so the first step of checking each level, so that is login, that is correct. But
Yes, sir.
for each level, you have to now go through each of these elements on that level. Okay, so if you're on, let's say, kth level, so
Yes,
you'll
sir.
have 2 raised to power k elements on that level.
Right. Complexity 2 Ah, so the we will use binary search,
Mm-hmm.
the best search. Basically, we can also use other quick sort and other search in Python. It uses order of login time.
Mm-hmm.
So our time complexity would be order of login. We just have to use a simple search algorithm and keep comparing the min or max element, whatever the requirement of the question is. So the net time complexity, one is of course order of login level wise, and then element wise in that and that in that particular level would take login. So login plus login would be log.
So you're correct about the level part that they are going to be log n level, but for each of the level, it's not going to take log n. It is going to take basically the number of elements that that level holds. Okay, so you basically have a summation 2k log n, and summation of k is varying from 0 to basically log n, and this will basically come out to be on. What you're essentially doing is going to each of the levels and checking all of the elements. Now, because there are total n number of elements, so you are going to be doing this checking n number of times, and your algorithm complexity will be on.
Okay. We have to check element by element,
Hmm.
because they are all
Yeah,
independent. There is no
yeah,
logical relationship
exactly. Yeah,
between.
yeah.
Yes, right. Right.
So basically, if you have to, let's say, find a successor for 25, okay, so you only know, because it's a min heap, you know that 25 successor cannot be its parent, okay, because the parent is going to be less than 25. It's not going to be the grandparent or the root. So what you know is that you don't have to check 17, 2 and 1 here, because you know that those are certainly will be less than 25, so they cannot be successor of 25. Okay, now the remaining nodes 100, 19, 36, 3 and 7, so these can be less than or more than 25. There are no constraints on them. Okay, so because of that, you can only eliminate uh, out of the whole n, you can only eliminate log n elements while calculating successor, basically, which is 1, 2 and 17 here. Okay, so you are almost checking all of the elements to find successor. Okay, and the same thing is true for predecessors also, and it is also true for max heap also. So in min heap and max heap, so this is given max heap, and the same fact is true for it, that if you need to find successor or predecessor, you'll have to check almost all of the n values. Okay, and checking each of these values individually only will tell you what the exact predecessor and successor is. So these data structures do not give you any advantages compared to basically to compute these predecessors and successors, and both of the operations are O in time, so C is the correct option here. So if it is not clear, you can ask right now, like if the whole, how are we going to search for elements, or why is it coming to be ON, or why is there not a more efficient algorithm? Like if any of these parts are not clear, just ask right now.
Yes, sir. Thank you.
Okay, fine. So these were the problem set for this week. Okay, in case you have any questions regarding the topic itself, so you can again, as usual, post it on discussion forum or WhatsApp group. Okay, fine. In case you guys don't have any more questions or doubts, we'll end the session here.